So engineering forces. So how many? As many as the problem requires. Sometimes, by the way, sometimes just one, sometimes two, three, four. It depends how complex the thing gets. Okay? There are many of these forces, since it really depends on what kind of physical situation is being studied. However, here are the only ones that we really care about in this course. What is this one called? Gravity, not gravitation. Different, related, but not the same. Number two. Okay, don't ask me why is it called, what's so normal about the normal force. Just relax. I'll tell you why it's called normal force. Number three. How many of you have heard of tension? Tension force. Number four. Could be your worst enemy, could be your best friend and lifesaver. Okay? Friction. Is friction good? Yeah. In 2 months, when you're driving in the snow and you want to really brake, that's going to save your life. Okay, we'll talk about that. Last one. Applied force. Applied force. Those are the 5 engineering forces that we really need to understand in this course. Gravity, normal, tension, friction, applied. Okay, so we have a slide for each one. Number one. Question, everyone. Can someone remind us how did we define gravitation? Gravitation is the attraction force between what? Between what? Did I tell you what the 2 objects had to be, or I said any 2 objects? Gravity, everyone listen up. This is the important principle here. Gravity is so specific. Gravity has to be between a what? A what? A huge object and a what? Tiny one. But the tiny one has to be on the what? It has to be either on the surface or very what? Very close. How close is close? Well, we'll talk about that. There you go. It's the force between a huge object. By the way, it doesn't have to be a planet. You still have gravity on the moon. Is it as strong as the Earth, though? No, but it still exists. You might say, so you might say, oh, so it just depends on how massive the object is. Yeah, but there's another factor as well. Very important. Just give me a second. I can't tell you exactly how very close is very close by. I'm just gonna say this. As long as when you drop something on the when you drop something, it really goes fast towards the surface, that's what we call what? Close by. Question. When you are on the International Space Station, are you close by to the Earth? Really? On the ISS where Commander Chris Hadfield was? No. How about on top of Mount Everest? Are you still technically close to the surface of the Earth? Yeah. How about on top of the Eiffel Tower? See, and yeah. So you see, it's kind of a relative thing, but at some point you have to say, I am not close, because you know what? If Chris Hadfield dropped something in the space station, would it go down? No, it would float as much as he does. Okay? Okay. We have to use different symbols now. But what is still the symbol for any force? Capital F with an arrow. But now we have to start using what? Little what? Subscript. What's the subscript for gravity? Can you guess? Absolutely. Yes. Everyone, I can't emphasize this enough. This G has to be what kind of a G? Lowercase g. So now you might think, oh, is there something with an uppercase G? There sure is. So that's force number 1. Force number 2. Normal. Question. Probably the answer is no. Has anyone taken calculus and vectors yet? Okay. Ladies and gentlemen, the word normal in calculus and in vectors just means perpendicular. Seriously. Normal in vectors means perpendicular. And that's why this force is called the what? The normal force. Everyone, if I look, did I hit the board? Was there a force from me to the board? Did the board hit me back? Oh, it did. It did. I felt it. Oh, yeah, I did. Did the board act back on me? What is the most famous Newton's law? Every action has a what? Here's my action. What's the proof that I have reaction? My hand hurts. Do you see what I mean? I hit it. It also what? But how did it hit me? Angled or straight out? I hit it in. It hits me what? How is the surface of this board relative to this marker? What's the angle between the board and the marker? 90 degrees. What does 90 mean? Perpendicular also means what? I just told you something from grade 12 calculus. Okay? So it is the force, a surface. By the way, anything that looks like a plane, even your hand. Push. No, push with a finger. It's like what? The fist and the what? And the board. Same thing. That's a plane. You're pushing. It's also what? Pushing back. Do you see what I mean? But he's pushing perpendicular in. My hand is also pushing what? Perpendicular out. Is it making sense? That's it. So, flat plane is all we need here. So, question. When can you only have normal forces? When you have what? You have to have a flat plane involved, and it's being what? It's being acted on as well. Any guesses for the symbol? G for gravity. Yeah, it's an N. Everyone, I like to use capital N. I've seen books with small n. I like to use capital N. Okay. Asser, what's force number 3? Tension force. Everyone, question. Is this under tension? What could happen if I tense it too much? Snaps, breaks, cracks, whatever. Tension? Is this tension? Is this tension? What do you call? What am I doing to my skin? What am I doing to my skin? Or what's another word for pushing in? Starts with C. What's the opposite of stretch? Compression. Compression, stretching. Okay, how about this? How about, what am I doing? Am I putting the lanyard under tension? How can you prove it? Once you let go, what's going to happen? So what did I do to this? Starts with a T. What kind of motion is this? Twisting. Anything that could withstand stretching, compressing, or twisting. By the way, does anyone know one word that could stand for all three? What do you call it when you, by the way, just a question here. When you, listen up, everyone, eyes on me. Is the mass changing or the shape? Does anyone know what do you call it when only the shape changes but the amount of particles stay the same, like mass? Starts with D. What happens when a baby is born with incomplete limbs? Deform. Deform is the actual technical term. Deform is the actual technical term when you change the shape. Can I deform this? Is this deformed? Could it snap? Could it snap? Could it? Yeah. I just have to keep what? It did. Right. I have a lot. Make sense? How many people work out here? Ooh, some people are just happy to say. Stretch marks. You see it? Lines, stretch marks. You know why? Because every guy here is going to do biceps curls every single day of the week for 7 days a week, right? What happens when you put the muscle under stretching and compression and tearing every single day? What happens to it? Does it ever go back? No. No. If you don't let it recover, does it ever go back? If you have a spring, actually no. If you have no. If everyone, if you have a rubber band, I don't have a rubber band, and you stretch it, sometimes you start seeing white in the middle, right? What is that white? Those are bonds broken, and they will never come back. That's exactly those. Is it making sense? You need recovery. You need to let it what go back a little. Is it making sense? That's what stretch marks are. Permanent deformation in the skin. Done. That's it. Okay? So, deformed is the word that stands for all of these. Here's my question. Question, everyone. Where can you see tension? Okay. Officially in this course in grade 12 and even in first year, you can see it in what? Can you put a rope under tension? Is it under tension? Because it could snap. How about strings? Well, this could be a string too. How about cables? Oh yeah. By the way, cables are made of what? Cables usually are made of steel, right? Or metal. You could still stretch that. Springs. Question for you. Is this under tension right now? It is. There's a lot pushing on it. Do you see what I mean? Compression tension. Everything could be under tension. Even, okay, question for you. Could you do this to a brick? You can't. Because a brick, is a brick elastic? This could take the hit, right? Could a brick take as much? Maybe more, but a brick doesn't bend. A brick what? Snaps, cracks, breaks. Do you see what I mean? That's the difference. Do you know what we call something that could deform and kind of like go with the flow? Elastic. What do you call something that doesn't? Starts with B. B-R-I-T-T. Brittle. Brittle materials. Am I putting this under tension now? Do you think it could bend? A little bit. But at some point, it's not going to what? It's not going to bend. It's just going to what? It's going to snap. That's my point. Okay, so literally everything could be under what? Under tension. No exclusion. Okay. What do you think the symbol should be? Symbol. Come on. I've seen, and I would actually advocate either one of these two. I will mostly use the second one. Okay? But I just, you know why? Oftentimes you're going to have a problem with a lot of ropes in it. So I don't want to say FT1, FT2, FT3. Just say T1, T2, T3, and so on. By the way, I want you to circle this, everyone. Circle this and say most common. Circle this capital T by itself and say most common. Most common. Oh, the second symbol, sorry. This one, and write most common. So I would urge you to always use T, not FT. Okay. Munir, what's force number 4? Friction. Can someone explain to me what friction is? Don't use any big words. What does friction always do? By the way, friction does one of two things. It could either what? Yes, sir. Listen up, everyone. What could friction do to your motion? Slow it down. What could friction even do? Again? So we'll say that stopping is the eventual feat of slowing down. What could friction even do? It could even stop you from starting to what? From starting to what? To move. Think about it. Is there friction going on? Yeah. Why would you hear the squeaking? Is it moving? Do you think I'm still pushing? Is my push big enough? But it's still there. which means what? There's still friction. Do you see what I mean? Friction could either slow you down once you start moving, or what? Or not even allow you to even begin what? Begin moving. Good. By the way, what kind of, okay, we have two kinds of friction, everyone. Listen up. We have this kind of friction. Look. I like to call this surface friction because it's an object on a surface. Was there friction when it was falling? Was it touching a surface? No. Okay. When something is surrounding something, we don't call that a surface. We call it an medium. Medium is anything you exist in. So there is medium friction, and what? Do you think we're ever going to deal with medium friction? No. We called it something before. Remember when we studied free fall? Air drag. We never care about drag. Drag is medium friction. Good. Okay. What is the symbol for friction? Any guesses? I mean, FF. You're right. Force of friction. Just make sure to make the subscript a smaller one. Sorry, like smaller in size and also in font. It's a lowercase. Okay. Last one. Ali, what's the last force? What's force number 5? Ali? Applied force. What's applied force? Okay. The easiest way to understand what applied force is it's any force that you cannot say it's one of the first four. Is it making sense? Everyone, applied force is not gravity. You know it's not the gravity. It's not the force by the surface, because that would be what? What's any surface force? No, the surface when you push on it. Nor normal or perpendicular. Please don't say perpendicular. It is perpendicular, but the official name is normal. It's not tension, and it's not friction. Anything else is called what? Which means what? Something else isn't the problem. It's usually a person pushing something or pulling. So it's a force with which an external factor, like a person, tries to change the state of a system. Technically, as I just said to Hale, for example, it's any other force that you cannot say it's one of the first four. Okay? From a technical standpoint, can you call the other four forces can you call them all applied? What do you think? Can you call gravity applied force? Yeah, it's applied by what? The earth. Can you call tension applied force? It's applied by my hand. Can you call normal applied force? Yes, it's applied by the surface. Like you're sitting down, like I'm sitting down. No problem. I'm sitting down. What's applying force on me? The chair itself. Exactly. So any force could be called what? Applied force. But because we have specific situations, we came up with what? With specific names. Only if it's away of these four names, we're just going to call it applied force. So what symbols can you use for it? Honestly, anything you like. The most generic one is FA. Another generic one, is F applied. Another generic one is, for example, if we have two people, for example, Art and Shira applying forces, I could call it FA and FC, or F Art and FC, F Shira. Anything. Just make sure that your labeling is correct. So I would say F whatever. Come on, where is it? There we go. Okay, so FA, F app applied, or F whatever. Okay. Let me just perfect. Okay. So the last thing we'll talk about for today is probably the most important one for now, which is the force of gravity. Okay. Again, we said that the force of gravity has to be between how many objects? One of them has to be very what? Very large and massive, and the other one has to be what? smaller, much smaller compared to that first one, but also where should be located? On the surface, or maybe not touching it, close by enough for the gravity to apply. Okay? Okay, is there any gravity force on the International Space Station? No, because it's very what? It's very far. But is there gravitational force between the Earth and the International Space Station? Yes, because they have mass. I don't care how far they are. Obviously, the further they get, what happens to gravitation? They get stronger or weaker? Much weaker. Okay, but at least there is some. Okay, so the force of gravity on an object at the surface. Okay, since we are most interested with the Earth, we're always going to take it with the Earth, although the exact same idea applies to the moon or absolutely any round celestial object that's big and heavy enough or very close by to the surface, is always given by the following formula. F small g, that's just a symbol, not a multiplication, equals, what does lowercase m usually mean in physics? Mass, or it could be uppercase, but let's say small. And g is what? Gravity. By the way, this is what? This is not milligrams. This is what? Mass times g. Mass times g. Fg equals mg. One of the easiest ones to memorize. Why? Because it rhymes. Fg equals mg. Done. That's it. But one thing to understand here. Your mass has to be measured or reported in what? What's the standard for mass in the international unit system? Nope. Not grams, not pounds. So that just leaves what? Kilograms. And obviously G is what value? But what's the value? 9.8 in what unit? Meters per second squared. That's why this equation right here involves the 3 units, kilograms and meters and seconds, which are basically the 3 major units in the international unit system, SI. Okay? All right. So Fg equals mg. All right. Another name for the force of gravity on an object is simply the what? The weight. So now you know, once you do physics, you should always distinguish between weight and what? Weight is not the same as mass. Exactly. Huge difference. They're related, but they're not the same. In other words, weight is, this is already given for you, this definition, the amount of force by which an object is pulled down towards the center of the planet. That's the definition of weight. Many teachers don't like straight down. Many teachers don't like straight down. They always like what? Towards the center of the planet, to remove any ambiguity that direction anywhere physically is important. It's just towards the core or the center of the planet. But I know you understand what we're talking about when you say straight down. Why is there no symbol for weight? Because we just said weight is just another way of saying what? Force of what? And force of gravity already has what symbol? Fg. Okay, here's another. Okay, let's play devil's advocate. Why can't we use W? I mean, it's weight, and we usually pick the first letter. Why can't we use W? Is there another thing that W is used for? Yes. What do you use for W for in math or geometry? Width. So that's already been taken. How about physics? Who remembers of grade 11? Okay. Watts as a unit. I'm talking about as a physical symbol in a mathematical. Remember, unit and symbol are not the same, right? For mass, the symbol is m. The unit is kilogram. Watts, like you measure the for light strength, for example, is a unit. I'm talking about a physical symbol. Who remembers it? What was the third unit in grade 11 physics? Energy and no, not no, not wavelength. Work. Energy and work. W is the symbol for what? For work. It's already been taken. Do you see what I mean? It's already been taken, and there's really no need for it because it's just force of gravity. There we go. Fg. So if I ever ask you for force of gravity or weight, don't be fooled. I'm asking you for the same thing. It's like in math when they ask you for what? How many people know how many everyone's doing functions here? X-intercepts. Raise your hand if you heard X-intercepts. What's another name for X-intercept? Zeros. So when the teacher asks you for zeros or X-intercepts, are they asking you for two different things or the same thing? What's the third word for them? There are 4 words for X-intercepts and zeros. There are 2 more names. Say it. What? No, domain. Remember, domain is just how big the x-axis is. Amar, roots. Roots. What's the fourth word? Solution. Because that's your solution to the equation equals 0. That's why. So solutions, roots, x-intercepts, and zeros are all the same thing. Okay. Who can define what mass is? In the easiest way possible. Don't use any fancy big word. If you have a younger sibling asking you what exactly is mass, sure. Anything that occupies space. Okay. But you're not describing. But that's not the mass itself. That's the object. I want you to tell me what mass is. Like if I ask you right now, okay, what's your mass? You could tell me, for example, 160 pounds. Yeah, what does that mean? Or like, for example, 65. Sorry, about 70 kilos. What does that mean? Why is your mass, for example, let's say your mass is 70 kilos and your mass is 65 kilos? What does that mean? Like when you think about it, what does that mean? By the way, does it mean that if you have more mass that you're occupying more space? No. Now we're talking about density, right? You could have a bigger mass but a smaller what? Vo volume or size. That affects your density. I'm talking about just mass. Anyone? We defined it in grade 11. Which one is heavier, this or that? Okay. Which one's heavier? So which one has more particles in it? Definitely, for sure. By the way, what are the only 3 particles that are inside your body right now? You are not made of absolutely anything else. Think chemistry. What are the only 3 particles inside of you? Protons, neutrons, and electrons. So if you have more mass, do you have fewer of these things or more of these things? That's it. Mass is just what? The amount of what? Of substance inside of an object. That's it. If I take you right now to the moon and weigh you, would you weigh the same or less? By the way, how do you weigh yourself? You step on a what? You step on a what? Scale. What do you do to the scale? You're not applying force. What is making the scale get force applied on it? Gravity, because it's what? You're pressing the spring down. Can you weigh yourself in space? No, because you can't what? You can't press on it. Do you see the difference between weight and mass now? If I take you right now to the moon and you step on a scale, do you still have the same mass inside of you? Inside of you, yes. But do you press on the scale the same way? No, because the moon is what? Weaker gravity. Is it making sense now? Mass is how much inside of you. Weight depends on the planet. Okay, so mass is the amount of, you see, I'm giving you 3 words for it. Matter, or substance, or stuff. Well, guess what? We're all made of the exact same stuff. 3 things. Protons, neutrons, and electrons. Sure, yes. But here, no. But here's the thing about the word particle. You you do know, or maybe don't, but there are so many particles other than what? Protons, neutrons, and there are actually, I think, 400 particles. 400 particles. 3 of them are the most common ones, and other ones are, occurring in like solar flares, deep space, and cosmic rays, and so on. But the ones that make us up are like protons, neutrons, and electrons. That's why sometimes they get Nobel Prizes for actually discovering a new particle or theoretically predicting the existence of one. One thing, everyone, one thing to know about mass. Mass is always what? Constant and fixed. Weight could what? Weight could fluctuate or change depending where you are on a different planet, how far you are from the surface of the planet, and so on. Although in some problems, what could happen to mass? It could actually what? It could change. How? Something blows up, a chemical reaction where things come together. Now you have a bigger, which means usually a more massive molecule. Okay? But you will actually know when mass changes because the question will explicitly say that. Okay? All right. Let's just quickly, you don't have to do the last slide, it's already filled in for you. So the major differences or similarities, I guess, or comparison points between mass and weight are mass is always measured in what? It could be measured in pounds, but then you're not doing it standard. You have to convert. Weight is always measured in what? Why is it newtons? Because technically it's a what? It's a force. So it has to be in newtons. Second thing, mass is always what? Unless you're told it's not, but you always assume it's constant. Weight is potentially what? Because I just told you about the moon example. Okay? Another way is to say that mass is the same everywhere unless you internally change. Weight is dependent on location. Last one, mass is not a force. By the way, does it make sense to say that my mass is 150 pounds pointing northwest? That doesn't make sense, right? Which means what? It's not direction dependent. What does that mean? If something does not need a direction, not only does it need, should not be given a direction, what do you call that? A scalar. Perfect. Weight is a force. Scalar. Why do you think I'm saying weight is technically a vector? Do you think I'm ever going to bother you in this course asking you which way weight points? No, weight always points what? Down. So it is a vector technically, but we're always going to be interested in what of that vector, its direction or its magnitude. There you go. So that's why I'm saying always remember it's a vector, although you're just going to give me the magnitude of that vector. And that's it.